Ladies and gentlemen, probably we will start with our session. Let me introduce myself. My name is Myron van Damme, and I am from Czech Technical University in Prague. You know that the session name is Flood Defenses 2. We will have 6 presentations. All of them will deal with stability of air structure for water engineering. So it means mostly for dikes, levees, small dams, where the probability of failure due to, let's say, surface erosion or different sort of internal erosion is very sensitive one. And this type of the failure is typical also from the view of Eurocode 7 geotechnical design. He qualified this type of failure between the ultimate limit state, type of hit, hydraulic gradient failures. However, before we will start with, I need to inform you that the presentation in this room will be recorded on video for STOA, the Joint Water Research Institute of the Water Boards, provinces, and the Ministry of Public Works of the Netherlands. And all presentations will be available on the YouTube channel of TUA, and more information you can find on this leaflet, which is also front of the session room. And the first speaker will be Myron van Damme from University of Oxford, UK. And please, Myron, take the floor.
Thank you. I'd like to talk about a rapid method for predicting breach hydrographs. This work I've done as part of my PhD in Oxford, and it has been supervised by Mark Morris and Mohammed Hassan from HR Wallingford. So, to give a small introduction, there's an increasing risk of flooding out there. So system risk models are being developed to determine how we can best make investments and where we have to increase the dikes and where not. These system risk models require numerous amounts of calculations and runs. So all the components of these models have to be kind of fast. They have flood spreading models which are reasonably fast already, and you have river models, but there's not really a way to link the two together. How much water is actually entering from the river into a flood area? And that's kind of the aim of the research I've been doing. So, in short, the task was to develop a tool that serves as a link between the river flow models and the flood spreading models, and that delivers a breach volume. So, to expand a little bit on the challenge we were facing, there are numerous types of embankments. I just put a few photos on there already. And each of these embankments are built of a different construction material, and only if you're lucky actually know what kind of material they're made from. There's very little amount of field data available. If something happens, they usually take a few photographs, but that's about it. And the breach formation is a very complex, discontinuous and interactive process, and it's still very poorly understood. So to expand on the breach process, here you see a generic breach hydrograph. I've divided it into like 4 stages for now. In the first stage, the water is on the outside of the embankment is intact and nothing happens. Then the water level rises in the river and it starts to overflow. At that moment, the water will start eroding the embankment surface. First, the grass cover will fill, and also it starts percolating into the embankment itself. It may affect the geotechnical stability of the embankment. Then, the moment the erosion cuts through the embankment and lowers the crest, at a certain point it reaches the outside slope. At that moment, the flow will increase further. The vertical erosion, or the level of the hydraulic control, will go down. The flow increases and you get kind of very strongly contracting flow conditions. And then at a certain point you have a massive gap in your embankment, and the flow will increase, the breach will widen further and further, And this will continue until the water level in your flooded area reaches the same as in your river. So the solution, let me allow to jump already to the solution. A solution is Ariba. It's a very rapid model we created. It runs in around half a second. And it delivers a time-dependent development of the breach width, the breach depth, and it gives you a breach hydrograph. It distinguishes between overflow failures and piping failures. And in the overflow failures, it also has a distinction between headcut failures and surface erosion failures. The grass failure is based on the method used in HR breach, an already existing breach model developed by HR Wallingford. And the piping failure also uses the same method as HR breach. So what is headcut failure and what is surface erosion failure? This is a very, very schematic overview of what actually happens in the case of headcut. So in headcut, the embankment is kind of made of more cohesive material, and it actually cuts back through the embankment, as you can see on the left side. In the Ariba model, it simulates this process according to the Simba model. I won't go into any further detail about the headcut model. Then, with regards to surface erosion, the landside slope has a limited steepness. So, what kind of assumptions did we have to make in order to make this model? Well, we first said, well, we have a very simple trapezoidal shape embankment made of homogeneous material. We assume that at a certain velocity, the grass cover instantaneously fills everywhere. We assume also that the flow over the entire embankment behaves like a one-dimensional flow. The crest also will erode downwards, and the landside slope will retreat towards the waterside slope. The breach widening, or the rate at which it happens, is a function at which the crest erodes downwards. There's no equilibrium transport conditions along the landside slope. Well, the flow is continuously increasing, so this is kind of a valid assumption, we would say. And the slope gradient of the landside slope is limited. Will be limited to the initial slope angle of the slope itself. Then the following assumptions. The soil erodibility is equal everywhere along the embankment. We assumed it's a homogeneous soil in the embankment, so hence this assumption. And we also assumed you have a fixed side slope assumption. So you just say the entire embankment is kind of, the cross-section of the embankment is just like a rectangular shape, and it just goes down and widens. And no erosion below the foundation of the embankment. Maybe this is not totally valid, but for the shape of the hydrograph, it has a very low or minor influence. So if you put all this kind of, and you trick it around a little bit, you can find a few equations. We start off with the erosion equation. We say, well, use the erosion equation to calculate the erosion rate. The erosion equation says, well, you have an erodibility times shear stress. The shear stress is, again, a function of the velocity squared times some other parameters. I won't go into much detail right now. And the velocity over the crest is given by this function, 2/3 of the gravitational constant times the difference between the water level in the river and the crest height. And then you have, along the slope, you assume, well, you start off with the critical depth, and it goes to the normal depth according to the equation of Bélanger, and then you can find a function for your velocity. So if you put the function of the velocities in the shear stress equation, and you put that in the erosion equation, you can model the entire process only using two equations, which creates a very, very fast model. So what will happen if you test this model? We compared this model, or the outcomes to the model, with the HR breach model. This Ariba model takes around half a second to run. HR breach model runs take around 10-12 minutes. For a crest level 6 meters and a crest width of 6 meters, and an erodibility of 5 cubic meters per second, centimeters per second, sorry, and the slopes on both sides are 1 in 3, you get this result. It's kind of perfectly overlapping, so this is a very good result, we would say. If you have a little bit different input values, we have a crest level that's even higher of 12 meters. You're talking quite big an embankment here. and a crest width of 6 meters, and the same further values. We can see a little bit of a difference between the VAST model, Ariba, and the HR Reach model. But the time at which the peak discharge occurs is almost simultaneously. And the aim was also to come up with a volume, a breach volume. So if you just integrate along this distance, you can actually get a very good estimate using the Ariba model. Also, you can easily use the Ariba model also in time-dependent studies. But then probably we need to do some further study on the impact of the differences. The difference is, comes forward, we think, due to the effect of the landed slope. We say it has a limited steepness, but how do you deal with this limited steepness? Do you assume it takes a maximum slope of 1 in 3, or do you say it stays equal to the initial slope angle? This is where Ariba and HR Beach differ the most in these assumptions. Hence, this could also explain the difference. Then the impact experiment. We also tested a Ariba model against the impact experiment. What we did is we had the reports of the impact experiments. These were full-scale embankment breach experiments. They were performed in Norway. And we had all the soil data and the test reports. So we did, well, based on the soil data we have, we assume what would be the erodibility. And all the data we filled in, we came up with the maximum value, what it could be, and a minimum value. Also for the Manning coefficient, we assumed the maximum value, what it could be, and a minimum value. And we assumed a uniform distribution between the two, and then run the Ariba model 500 times and came up with like, okay, the value has to be lower than this and higher than this. So this value we found for the large range of input parameters, which are the maximum and the minimum value, is given by the blue shape, and it's also a horizontal line here. And then we said, okay, what if we halve these parameters? So we make the range a bit smaller, and then we found this green shape. And the red line here is given, that's the experimental outcome. And we can see the Ariba model is able, in theory, to predict the event quite well. So what kind of data requirements does the model have? It predicts the breach through simple and homogeneous embankments. It does not simulate, as of yet, very complex structures and structures made of composite different materials. And the speed of the model, because it runs in like a fraction of a second, does allow the user to play and make different runs and do some statistical analysis with it. It requires the definition of an upstream load, a hydrograph of a river or something like that, the embankment geometry, and also the embankment soil erodibility. In the UK, most embankments, they don't actually know what the soil consists of. So we have an embankment here, we know this is approximately the shape of the embankment, but they don't know what kind of soil it's made of. So even the erodibility of the soil, this is something we can recommend further studies has to be done to. And assumed failure mode, you also have to give this to the model. Is it going to be piping, is it going to be headcut erosion, or surface erosion? If it's made of cohesive soil, you can almost assume it's headcut. If it's made of sandy material, you can assume it's surface erosion. And if the water level remains below the crest level, well, you can say it's going to be piping. These are very coarse assumptions, of course. So as conclusions, the Ariba model is a fast-running, simplified breach model that has been developed and is suitable for use within system risk models because of the speed at which it runs. It deals with gross protection failure, surface erosion failure, headcut erosion failure, and piping. The incorporation of Ariba within system flood risk models will be a significant improvement over the current situation. In the current situation, it was usually a matter of this: we have an equation, or we say something goes wrong, we assume that there's a gap in the embankment of 10 or 15 meters wide, and we calculate the flood volume through it. Ariba generates an output hydrograph that falls within the bounds of uncertainty given by the input parameters, and Ariba is compatible with 1 and 2D river channel and floodplain hydraulic models. Thank you. Are there any questions?
Thank you very much for your nice presentation, also holding the time exactly 12 minutes. So we have now 3 minutes for the question from the floor. First one, please your name and affiliation.
My name is... I'm Gerard Beaufort, former Rijkswaterstaat. It struck me that the dike base does not erode at all. From Holland's experience, we know that large gaps in dikes exist after a breach, especially in the underground. Have you considered that possibility as well?
Sorry?
Erosion of the underground of the dike base has not been considered.
No, it has not been considered because we don't consider it to be a massive impact on the hydrograph shape. It does occur, but it's not a factor or parameter we consider to be of massive interest.
In the 1953 dike breaches, that was the main cause that they could not be closed soon. They became 30 meters or more within 24 hours.
Yeah, but that has something to do again with what happens after the breach has occurred.
No, it's a part of the breaching process, I think, that the subsoil also erodes. Subsoil under the dike.
Under the dike?
Yes. It's not rock most of the time. It's alluvial soil most of the time.
Probably you are speaking about the piping.
This is piping.
No, erosion.
Yes, internal erosion, which we sometimes call piping, called subrosion, some sort of the internal erosion, in fact. Yes.
No. When the dike material has disappeared, the erosion at that location of the breach does not stop. It continues to erode in the subsoil.
Yeah.
That's what I tried to explain.
Yeah, but at that moment, if the dike has disappeared and this is already a breach in the dike, it will continue to erode in the subsoil. But at that point, the erosion of the subsoil itself will have a minor impact on the shape of the hydrograph through the breach. It will affect the shape of the embankment at the end, but that's not really what we're interested in.
Well, it depends on the river water level at that moment. It depends on the amount of water available to erode the dike and the subsoil.
Can I make a comment? I think the objective of this model was to come up with a very simple, rapid breach model for a rapid hydrograph that could go into system risk models. So it's not designed to predict internal erosion and the breach initiation and so on. It's in effect.
Quantity going through the breach what I'm interested in.
Yeah, and I think you get into site-specific cases whereby if the breach isn't drowned, if the floodplain level hasn't risen at all, then you would get erosion into the foundations potentially. It depends on the local topography, doesn't it? So I think you're both probably right to some degree. It's site-specific.
So we have no space for a second question. Thank you very much indeed. Once more. And